Welcome to qnawire.
We have a simple ideal Rankine cycle. We're putting in, let's see here, 40 megawatts of heat. Uh, or heat energy per, basically, megajoules per second of heat. Um, we can start doing our analysis just as we normally do. We know we have a saturated liquid at 7.5 kilopascal, so we can get the enthalpy, the specific volume, and the temperature down here, which means we can get the work that the pump did in getting this pressure up to 6 megapascals, and then we can do an energy balance on the pump to get the enthalpy at the exit of the pump. At point 4, we were told that we have a saturated vapor, and again, it's at 7.5 kilopascals, so we can get the enthalpy and the entropy. It's an ideal turbine, so the entropy, there's an isentropic. So we have the pressure at here was 6 megapascals, and we know the entropy now is the same as it was at 4, so we can get an enthalpy and a temperature. And from that, we have enthalpy at all of our inlets and outlets, so we can get the power, the heat, the specific heat in the boiler, the specific heat out in the condenser. The difference between these is the net work that the system put out. And then this divided by this is the efficiency, which turns out to be 48.6%. Let's see here. We can get the power output, which is the efficiency times the rate of heat transfer going in, and that winds up being 19.4 megawatts. Again, we know we can then get the let's see here. What else do we have? The difference between this and this is the amount of heat that we dumped out in the condenser, and that winds up being about 20.6 megawatts. From there, we can get we have cooling water coming in as our condenser. So we want to know what the mass flow rate of the cooling water is. And we're assuming that it leaves it leaves the condenser at the same temperature as the feed water. So that's why we got this feed water temperature here, and it came in at 15 degrees C. And again, we can take this difference because the difference in degrees C and the difference in Kelvin is the same. So I didn't convert them to Kelvin, but again, it's probably best practice is to always just convert everything to Kelvin so you don't have to, but the difference is the same. Delta in K is the same as delta in degrees C. And then the heat capacity of water, and that divide that, so this is the energy, the specific energy flowing change in the cooling water. So take that, the rate of heat transfer going into the cooling water and divide it, and we'll get the mass flow rate of the cooling water. And so we need about 195 kilograms per second of cooling water to make it in our condenser.